Welcome back, class. So today we are going to continue our discussion with some aqueous reactions, and we're going to look at a couple of different kinds of aqueous reactions, what we call acid-base reactions, and then we're going to look at some reactions that produce a gas. So first of all, let's look at these acid-base reactions. So if we think about these as taking on sort of the generic form of our acid here and our base here, when an acid interacts with a base, it will always form water, right? And some, what we'll call an ionic compound. Now, sometimes you might hear this referred to as an acid plus a base gives you water plus a salt, or in other words, an ionic compound. Now, generically, this is referred to as a neutralization reaction. So an acid-base reaction or an acid-base neutralization reaction, because the base is neutralizing the acid. Now, what is an acid? What is a base, right? Well, we've talked a little bit about acids when we named them, and we learned a little bit about them. If you've had a chance to watch the video that I posted either before you do this or after you do this, it talks a little bit about your basic properties, right? Or your basic properties of an acid and a base. So acids are sour, bases are bitter, etc. But what about their chemical definitions? Well, there's basically two sets of definitions. The one that's actually defined in your textbook in this chapter is what's called the Arrhenius definitions, and these are some, definitions that are based on more the structure and the function of the acid and the base. And so what they say is that an Arrhenius acid is a substance that, here, let's do a different color, I don't like this, that's too much red, is a substance that produces H plus ions in water. Or if you want to, for these, we could call this an aqueous solution, right? So an acid is a substance that produces H plus ions in water. Now, I'll note down here that when we use H plus, what really this is referring to is hydronium ions. And I talked about this a little bit in a previous section when we were talking about electrolytes, right? And we talked about how when an acid ionizes in solution, it reacts with the water and produces hydronium ions. So when we use the term H plus ions in these definitions, it's a shorthand for this hydronium ion that's formed when an acid ionizes in water or reacts with that water. Now, a base is a substance that produces hydroxide ions in water or in aqueous solution. Now, I can give you we can write an example here. So I've already written an acid example, but I'll write another one here. And so, for example, we saw this reaction earlier in the chapter where I said HCl, when it's dissolved in water, reacts, ionizes to give you H+, or again, hydronium ions, plus Cl minus aqueous solutions. Now, if we want to talk about a base, we can use, for example, sodium hydroxide. When that's in aqueous solution, it produces hydroxide ions plus, in this case, sodium cations. But of course, the key ion here, right, is either the hydrogen ions or the hydroxide ions, right? These are the important ions that either make something an acid because it's producing the hydronium ions, or a base because it's producing the hydroxide ions. Now, a more useful definition of an acid and a base that we don't define at this section of the book, but I'm going to go ahead and define it so that you're familiar with it as maybe you're watching other videos or looking at other things about acid and base, and maybe you hear this terminology, and that is the Bronsted Lowry definition of acids and bases. And we will use this when we talk about acids and bases next semester when we do a lot more acid-base chemistry. So an acid is an H+, or what is sometimes called a proton donor. And a base is an H+ acceptor. And at this point, that's kind of all we need to know about the Bronsted Lowry, is that it looks at acid-base reactions as an exchange of H+ ions. So just to give you a quick example here, if I were to look at, say, HCl dissolving or reacting in water, right, as described, and it formed hydronium and Cl minus. What we can see is that an H+ moves from here to here, right? So the HCl is functioning as the acid, right? The H+ donor, and the water is accepting it and functioning as the H+ acceptor to generate, in this case, the hydronium ion and the chloride ion. So we can look at acid-base reactions as an exchange of H+ ions, and this is sort of the Bronsted Lowry approach to looking at them. Okay. Now, while we don't need to memorize acids and bases, we can be familiar with some of the more common ones. I will tell you the ones listed here in black, right? These are your strong acids, right? There are only 6 of them. Eventually, it's a good idea to know these, right? It just makes it easier when we start doing chemistry to understand, oh, that's a strong acid. This is a weak acid. Remember when we talked about electrolytes earlier in the chapter, that what we mean when we say strong acid, or we'll say strong base here, we just means that it either fully ionizes or dissociates, depending on what kind of compound it is, into ions, right? So it's a strong electrolyte, forms complete formation to ions, whereas weak acid or weak base is a partial ionization. So only part of the acid molecules go on to form ions. And so lots of examples of weak acids. You might have heard of acetic acid in vinegar, hydrofluoric acid, right? These are a couple of examples of weak acids. Bases, right? These are your strong bases. They're your early metal group 1 and group 2. Most of your group 1 and group 2 metal hydroxides are where your strong bases come from. Right? Notice these are all ionic compounds. They're going to completely dissociate to form your hydroxide ions and accompanying positive ion in solution. The most important weak base, or most common weak base, right, is ammonia. So at this point, again, we're just kind of becoming familiar with these ideas of acids and bases. Now, let's jump ahead now and actually look at some acid-base interactions, reactions, and try to predict products. So, like we saw with precipitation, the examples that we saw earlier in the precipitation reactions, these acid-base aqueous reactions are going to follow that same double displacement pattern that we saw. So we can use sort of the same approach to analyzing these. We can identify the ions that are present. Now, we have an acid here. So, really, if I have an acid, right, the two ions are going to be H plus, and then whatever the negative ion is, so in this case, Cl minus. Now, remember, these are all aqueous. I'm just writing these a little bit shorthand. Now, my base, in this case, barium hydroxide, it's an ionic compound, strong base. Right? It's going to break apart into my barium ions, right? Being in group 2, it's going to form a 2 positive charge, and get some hydroxide ions, or 2 hydroxide ions here that are going to form. So I've identified the ions present. What do I do now? I do my double displacement. I swap my ions. So again, the positive ion from the first one is going to combine with the negative ion from the second one. And again, what did I say about the neutralization? One of the products is always water. So the H plus is going to combine with the hydroxide. And we're going to form water. And then we have the other two, the second positive ion combined with the first negative, so the barium and the chlorine combine. We have a 1 to 2 that we need. So we're going to write the formula as BaCl2. So now I've written my products. I need to balance my equation. So I can see here that the Cl, right, I got 1 and I got 2, right? So I need to put a 2 here. Now, notice I didn't try to balance the hydrogen first because I have hydrogen in a bunch of different places here. So I'm going to balance the barium, 1 and 1. Now I can start to balance the hydrogen. I got 2 hydrogens here. I have 2 hydrogens here from the 2 hydroxides. So I need 4 hydrogens. I have 2 over here. So I'm going to need 2 waters. So to give me 4 hydrogens, that gives me 2 oxygens. I have 2 oxygens here from my 2 hydroxides. So now I'm balanced. Okay. Now, what about states of matter? Well, the states of matter here are going to be, water is going to be a liquid, right? Because we're doing this in aqueous solutions, low temperature. It's going to form liquid water and the BaCl2. Now, this is either going to be aqueous, or it is possible that we could also have a precipitation going on here. So you could check your solubility rules. Now, the more you become familiar, the more easy it'll be to recognize some of these as soluble. Now, I know that chlorides are almost always soluble except for a couple examples, silver and lead, most important ones. So, likely this is going to be aqueous, and it will be most of the time for these acid-base neutralization reactions. But there is the possibility you might form something that is a precipitate. So our molecular equation, right here, right? We have our balanced molecular equation. So what about the net ionic equation? Well, we have a reactant, so let's go ahead and finish out the complete ionic equation. So let's write our products here. So we got our 2 waters, and we have our barium. Now it's aqueous, right? So that means we're going to break it apart. Now to get to my net, of course, I need to get rid of the spectator ions. So what are the spectator ions? Well, we have barium ions here, barium ions here. We have chloride ions here. We have chloride ions here. Now, of course, because of the balancing, right, we really have a 2 here and a 2 here. So those are going to cancel out. So what are we left with? Left with 2H plus 2OH minus gives me 2 waters. Now, most likely we would write this back. We could simplify this. It would be perfectly fine to simply write this as H plus OH minus goes to water, right? We could cancel out all those 2's since reduces down. That's liquid. And these would be aqueous. Okay. So let's try one more here. So H2SO4 plus lithium hydroxide. So again, we're going to do the same thing. We're going to break this down. We have 2H plus ions plus SO4 2 minus ions. We have a lithium plus ion plus a hydroxide ion. Now, we combine the positive ion from the first one with the positive ion from the negative ion of the second one. And again, just like we've seen in all of these, right, one of the products is going to be water, right? So we're going to generate water, right, and we know that's going to be a liquid. The second compound, I'm going to combine the negative ion from the first one with the positive ion from the second one. So we got the lithium sulfate. So we need 2 lithiums to match up with my sulfate. So we're going to have plus lithium 2SO4. Now again, we're going to consult our solubility rules to see if this is soluble, and I can tell you that it is, because lithium salts are always soluble. So we got lithium sulfate as our product. So if I wanted to write the molecular equation, right, it would be H2SO4 aqueous plus lithium hydroxide aqueous goes to water liquid plus lithium 2 sulfate aqueous. Now we have to of course balance this, and we see that the lithium, we have 1 here, 2 here, so we're going to need a 2 in front of the lithium. And we can see that we now have 4 hydrogens, so we're going to need a 2 here in front of the water, and that should balance out with my oxygens, my sulfates balanced, so that should be my overall balanced equation. So this is my molecular equation. Now for my net ionic equation, I have to write my complete ionic equation. So if I rewrote my complete ionic equation, it'd be 2H plus SO4 2 minus plus 2 lithium plus 2 OH minus goes to 2 waters plus 2 lithium pluses plus SO4 2 minus. We get rid of spectator ions, right? So we get rid of our lithiums, we get rid of our sulfate, and again, what are we left with? 2H plus 2OH minus goes to 2 waters. And again, we can simplify this to give us H plus aqueous plus OH minus aqueous goes to water. Now, what I want to point out here is, notice we've done 2 examples here of acid-base neutralization ions reactions, and we've written the net ion equations, and they're identical. And this is what you'll find, is that every acid-base neutralization has the same net ionic equation as long as the salt that is formed is soluble, right? And so we start to see these patterns. They can help us, sort of simplify things, right? And it's pretty easy to understand that an acid-base neutralization will always have the same net ionic equation. The hydrogen ions from the acid reacting with the hydroxide ions from the base to neutralize to form water.